Let's talk about Cartesian products. So a Cartesian product of two sets, A and B, can be written as A times B. And A times B is just notation for all of the ordered pairs x comma y, where x comes from my first set and y comes from my second set. So as an example, if A is equal to 1, 2, and B is equal to 1, 4, then the Cartesian product A times B is just going to be equal to every possible way of collecting one thing from A and one thing from B. And so that would be 1 comma 1, 1 comma 4, 2 comma 1, and 2 comma 4. And so there's 4 options total. And so now if we consider how many elements are in the Cartesian product of 1 through n times 1 through m, you can see that there's n ways to pick the first element in my ordered pair and m ways to pick y, the second element of my ordered pair, if I'm writing my ordered pair as x comma y. And so that means that there's n times m total ordered pairs. And so again, the way of counting this is to try and come up with an algorithm that would produce the ordered pairs and then see how many ways there were to run your algorithm total. And this is a little different than what we've seen before because these are ordered pairs. And so I don't need to divide by 2 or do anything like that because the ordered pair 1 comma 2 is not the same as the ordered pair 2 comma 1. And so there's no cancellation due to symmetry here. Okay, so now I want to spend a little bit of time visualizing Cartesian products. And so let's say that we're talking about the Cartesian product of R cross R. And so R cross R, that should be the set of all of the ordered pairs x comma y, where both x and y are in R. And so if I draw a picture of that, then I could really have an x-axis and a y-axis. And this is just telling me that they could be any real number, both of them. And so in other words, this is just notation for R2. And this is just the Cartesian plane. All right, so now let's talk about R cross Z. And so this is only slightly different. It's still the ordered pair is x comma y, but now we need x to be in R and y to be in Z. Okay, and so if we draw this in a plane with, again, the x-axis and the y-axis, then this is telling me that my x values can be anything from left to right, but my y values have to be restricted to these hash marks right here because it has to be an integer. And so if I draw out what that means, if x can be anything but y has to be restricted to these hash marks, then really I'm just going to get a set of horizontal lines. And they are the horizontal lines placed at integers. And so in other words, at integer heights. Okay, so now that we have some visualization of a couple basic examples, it's also going to be important to identify when we have a set that is a Cartesian product and when we have a set that's not. And so let's consider a couple examples. The first one is the list of all ordered pairs where y is restricted to be between 0 and 5, but x is just inherently anything, and here it's implied that the universe is the real numbers. And so if I draw this out, then it's saying that y has to be between 0 and 5, but then x can be anything. And so I can sort of sketch what this is. It's just going to be this infinitely long rectangle that goes to the left and to the right infinitely. And so it is the case that I can express this as a Cartesian product where the restriction on x is that it just has to be any real number, and the restriction on y is that it has to be between 0 and 5. And so this is the Cartesian product R cross 0, 5. And in general, it'll turn out to be the case that Cartesian products are typically the union of finitely many rectangles. Although it turns out that the rectangles can't interact in weird ways, and you'll see more about that in some of the problems in this worksheet later. But for now, let's look at one other example where we have this ordered pair x comma y, where x has to be strictly greater than y. And so in order to picture this, first I'm just going to draw the line where y is equal to x, or a squiggly mess, since apparently I can't draw straight lines. And then I just want to draw the region where x is greater than y, and so that'll be the stuff that's to the right of this line. Okay, and so you might be able to see that this is not a union of finitely many rectangles, and so it's not a Cartesian product. And so now, though, we want to prove that this is true. And so often to show a proof that something is not true, we'll do this by contradiction. And so let's say that this is sum A cross B. All right, and so now we want to figure out a way of showing that this definitely can't be the case, that this is a Cartesian product A times B. And the way we're going to do that is we're going to find a couple points that are in this Cartesian product that imply that another point has to be in there. And so what I'm going to do is I'm going to look at the point 2, comma 1. And I'm also going to look at the point down here, which might be, let's see, -1, comma -2. Okay, and so this point right here has an x value that's bigger than the y value. And it was taking me a second because I always flip around the inequalities when they're negative numbers. And then this one has the x value again being greater than the y value. Okay, and so we know that we have that -1, comma -2 and 2, comma 1 are both in A cross B. Right, and so if that's the case, though, then that means that -1 and 2 both have to be in A. And also, we would know that 1 is in B, just by checking out the second coordinate of this value right here. And so if that's the case, then that's going to imply that the point -1, comma 1 is in A cross B. But this is a contradiction. And the reason that that's a contradiction is because -1 is less than 1. So x is less than y here. All right, and so that's the end of this proof. It shows that if it were a Cartesian product, there'd have to be extra points in the set that weren't really there. And so this cannot be a Cartesian product.